Okay, we'll be studying today robots edge detection or edge detection using robots as it is known as in the domain of research actually. So let's dive right into it. But before getting into the specifics of edge detection using robots, let's understand what exactly is edge detection beforehand. So detection is nothing complex or like a lot of crazy stuff. Just a simple way of detecting edges. Though the definition might confuse you because it's using mathematical variety of mathematical methods. It aim at identifying points in a division limit at which image brightness changes sharply or more formally has discontinuities. This might be scary to hear, but it's nothing. We just need to figure out from in a particular point when does the image sharply falls. Okay, in this image, but in this instance, it just sharply falls down to it at the end of the day. Now, let's see. Uh, the points at which image brightness changes sharply are typically organized into a set of curved line segments termed edges. Yeah, that's what exactly detection is. Now, in a computer, we have an image in 3 by 3 grid or similar fashion. I'm just trying to mimic as well as I can. So let's say this is a pixel edge with high value, okay, this particular one, and this is the one with low value. Now there is a sudden decrease in intensity of the pixel. So this is termed as edge, not this pixel. More appropriately, this pixel will be termed as actually. Depending upon your requirement, you might need the white pixel to be your edge, or you might need a dark pixel to be your edge. But yeah, more typically, we consider these points as our edges. So, what are the different techniques of edge detection? We have the software edge, we have canny edge, the privet, and robot. And last, fuzzy logic methods. These are new methods, but now they are used. Canny is the most used among all of these, but today we'll focus on robot. Now, let's understand a short description about robot edge detection. It performs a simple, quick to compute 2D spatial gradient measurement on an image. Now, you will understand what exactly does it means. Simply say it will detect edge using a 2D mask rather than 3D, 2D mask rather than 3D mask that is used in various other techniques for color image detection actually. In its most common usage, the input of the operator is grayscale image as it is the output. As is the output, yeah. We'll feed a grayscale image as the input, and the output will also be a grayscale image. The only difference would be that the output will have edges instead of the entire image. The emphasis on the edges will be more. Now, the pixel value in each output represents the estimated absolute magnitude of spatial gradient of the input image at that point. Yeah. Now, in the magnitude image, since we are emphasizing on focusing on the image, the output of the pixel values which are in the image will be much more emphasized or much more clearly visible compared to the original image of that same pixel. Now, let's understand a briefly about robots cross. The robots cross operator is used in image processing and computer vision for edge detection. Yeah, just like it says robot cross is used in robot cross is used in computer vision edge detection. These are typically the most common use of edge detection. Anyways, now let's see. It was proposed by Lawrence Roberts. Yeah, the name of the scientist who proposed it gave it the robots edge detection. As a differential operator, the idea behind robots is to approximate the gradient of movement through discrete differentiation, which is achieved by computing the sum of the squares of differences between diagonally adjacent pixels. Now, discrete differentiation or differential operator should not be scared by these terms. These are nothing but they simply referred to as mathematically subtraction values. Since we are going by discrete differentiation, we do not need to bother about the actual d by dx or d by dz formulas, but rather a simpler form of differentiation or the most used form of differentiation that would be subtraction. Now, in theory, the operator consists of a 2 by 2 convolution mask as shown. The mask, as it mentioned in theory, it's in the part meaning of the term in theory refers to as, since the operator consists of a pair of 2 by 2 convolution masks, it is in theory you can improve it, increase it, decrease it as per your own requirement, maintaining the principles that was used to design that mask. And one mask is simply the other rotated by 90 degrees. You will see it. Okay, we have a mask, and you can see we just rotate this mask to 90 degrees. We get this one. The entire mask is rotated. Simply that the reason behind rotating a mask is actually pretty simple. If we have a vertical image and we want to find the horizontal edge, rather than creating a new mask, we just rotate the mask. Similarly, we have a vertical line, we just rotate it by 90 degrees, we get an horizontal line. So the idea follows that as only. Now, these masks are designed to respond maximally to edges running at 45 degrees to the pixel grid. Please do not focus too much on this thing. It's the basic idea is will detect edges till 45 degree. There's one mask for each of those two perpendicular orientation, that is the horizontal and the vertical one. Small, okay. Now this mask can be applied separately to the input image to produce two separate images, but if we don't need two separate images, we need all the images in a single image. All the edges in a single image rather than in two different images with two different edges. So what we do is we combine both of this and take the magnitude of it by the particular formula, that is square root of gx square plus gy square. In most cases, this formula is used, but in special cases, you can also use this formula, though the answer is approximate equal, but may depend in certain cases. Okay, now the angle of orientation of the edge is giving rise to the spatial gradient. Initially, what I was speaking from the very start, we had a term called spatial gradient. That is nothing but the angle in the direction of angle. Actually, it's a vectorized space in a 3D matrix. Perfect, but yeah, that's the idea behind it. So the angle of a particular pixel to which it is pointing, like whether it's horizontally pointing upward or vertically pointing downward. In an image space, there are ways an angle can point. Consider this pixel. Let's say this is a pixel. We can see it can point upward, down, this way, this, or even diagonal ways. So if you need to calculate the angle for your particular research references, you can refer to that as well. Now in this, if the orientation is 0, that means the direction is for maximum contrast. Okay, direction of maximum contrast is from black to white. In layman terms, this is simply say this is a black pixel and you have a white pixel. You have a white pixel. This would only refer to as moving from left to right, from a low to high pixel density. That's all. But if you getting that deep dive into it, you better understand the terms of contrast, brightness related to it, and various other intensity related terms. Okay, now as a user, we won't be interested in angle too much or the values that are present in the matrix grid. The thing that we'll be interested in will be the absolute magnitude or the final answer that we need will be the combined image of all with all of the edges visible. So there are the way two masks that we previously saw can be generalized into a single mask. That would be this. If you consider an image, okay, let's say if you consider a mask, a horizontal mask. So this one had +1 here, it had 0, another 0, and a -1 here. Now if we solve it, we get P1 plus 0 plus 0 minus P4. On further solving it, we'll get it as P1 minus P4. In this similar fashion, we can get P2 minus P3. Just as I said, it's just the addition of it. If we are considering the horizontal mask, this region will become dimmed as 0, and if we are using the vertical mask, this region will end up being 0. Let's consider a simple example of a numerical. We have an image. It's not an image. Let's consider a part of an image. The particular with the particular values, we apply the horizontal and vertical convolutions to it. Now let's say we consider this region and we apply the horizontal mask to it. So what will be the answer? That will be 3 plus 0 plus 0 minus 5, right? Which gives us the answer as minus 2. And if we convert the same image with the vertical mask, we get the answer as considering 0 plus 6 minus 3 plus 0. This in turn will give you as answer as 3, and you can move from this to this. We won't be considering this pixel as there's no value beside it. So we'll go till here and till this particular pixel. These are just basics of convolution. If you want to understand why we are going till that particular pixels only and neglecting the last row and last column, you can study more on convolutions. Okay, the output would be something like this. On gx, like initially we found minus 2, so we have that here. And for gy, like we found 3, we got our 3 here. Now we square both of these values, so yeah, we get gx square and then we get gy square. We will consider the square root, like so I told you, in many cases we tend to go by the square root method, but if it's rise and you have a lot of computation to do, you might end up choosing the module operator method, but we tend to go with that, so let's go with it. Yeah, the output values that we get are floating points. Images aren't of floating points, so we need to convert them to closest integer so that we can understand what the intensity of each image. Now if we consider bright pixels, we get edges like this, and if we are considering dark pixels, we'll get edge like this. So in our particular edge case, we have an image edge and something of this fashion. I know it does not make any sense, but yeah, it might end up being a part of larger edge that we will be using or referencing in the end. Now there are some examples of robot edge detection. You can see we have a gray image and then another gray image. It's not a gray image, it's actually a colored image, but after preprocessing, we get some edged images of both of these. You can see the actual images are hard to believe that this image belongs to this, but yeah, it is. There are a few drawbacks of robots, so yeah, that's the reason why there are other edge detection to begin with, but it has its fair share of drawbacks, and we'll see them in the next slide. Now, what are the advantages? Before saying anything bad about someone, we need to say good about them as well. So it's the detection of edges and orientation are very easy in robot edge detection compared to others. That's true. At the same time, the diagonal direction points are preserved. Yeah, in the robot edge detection, the diagonal points are preserved automatically by the numerical itself convolution method that we use. The disadvantage is very sensitive to noise. As you saw in the previous images, it was hard to believe the robot's detection. It was detecting those particular values that were not even edges, and which were edges, the detection mechanism was not working on it. And it's not, since it's highly susceptible to noise, it's not very accurate. A lot of the images that we get aren't completely noiseless or are discretely formed with, you can say they have discretely formed edges which can be easily detected. Now, these are some applications of edge detection. We use it in image processing, like machine vision. We have computer vision, and in the case of feature detection, machine vision, computer vision are not different as sorry, aren't similar things, but actually are different terms. Initially, the machine vision was considered to be a part of something which involves just viewing things actually. But as time evolved, this spelling is wrong, but let's go with it. The just a form of viewing things and a little pre-processing on it. But computer vision is a different thing. It not only does the pre-processing and viewing part, but it gives us insight from a particular image, and somehow you can use it to determine various other factors as well. It's mostly used in the domain of deep learning, and it involves a lot of convolution and neural networks in it. But as you study further computer vision, you will get to understand it. And there are other areas as well. We use feature extraction and feature detection. Feature extraction and feature detection, there are times when a particular feature is extremely different than the other. So we need to figure out whether that is there a need or is there some kind of edge data that differentiates both of these features. So yeah, that we use it. One common example is for ECG graph actually. Uh, we have ECG something like that. So when there's a cardiac arrest, there might be a case when this graph fluctuations. These particular fluctuations will form a different pattern. So before a cardiac arrest, how does this fluctuation happen and what's the edge value or the thresholding value when a person may end up going into cardiac arrest. So at that particular time, we tend to determine the edge value, and as soon as the pattern matches and it reaches to this particular edge values before the person goes into cardiac arrest, the doctors and the response surgeons can take the action. Now here are some references if you wish to study more about these things, and we have a link to collaboratory notebook where we view how exactly the robot set detection works. See it actually, it's an interesting thing. Let's open it up and we'll see the collab actually. It's an implementation of risk detection. I've already opened it. Let's just connect to our runtime. It won't take too much time, but we'll see an actual example how all of this edge detection works. So, okay, that's good. Now, by default, initially it does not have a library that I need called as image, but I am not using it anymore in the figure, so let's just remove the cell. Okay, now I'm writing this code in Python, so let's just load all the necessary libraries, and you can see I made robots both the horizontal and the vertical process. The reason here I use 3 by 3 pixels because it's a good practice to use 3 by 3 convolution matrix over 2 by 2, and the system libraries require it to be at least of 3 by 3 pixels. So we'll be going back that. You can use a 2 by 2 matrix. It's just a personal preference, nothing special honestly. Now let's read the image first. Okay, I'm directly reading it from the source. I just googled up some wallpaper image and it's reading it. Now, yeah, the initial read format will be either in Unicode or unsigned integer. Will be needed into float. You can use 32 or 16 as well. Using 64 just out of personal preference, and convert the image to grayscale. We do not need the color image, but the grayscale image. And this step does nothing special. It just normalizes the entire image. We need to have it in a standard format, so that's that. Okay. These are just some pre-processing steps to avoid any issues. Now let's just view the image. Uh, it's more or less similar to what you viewed before. Um, but no problem there. And then we can As you can see, we need to convert. Now, these are the vertical convolution steps. This is the vertically generated image, and this will be the horizontal generated image. If we run this, and now the implementation of the formula that we saw, square root. So yeah, we are squaring each of these images and then square rooting it, taking the square root of it, and that gives us a generated image, edged image. And let's view the edge image actually. Okay, as you can see, it's not this amazingly huge, but extremely properly detected edge because there was a lot of noise. You can see here, there is a lot of noise. These are minute, smaller pixels that does not makes any edges, so the system is kind of confused with that. But the region which has proper edge like this, you can say, I don't know what the term for this bridge is called proper, but yeah, this bridge you can see there are proper edges to it, and then this is now a noise does not mean only the green particles, it may also mean the color matchingness. Okay, now this is entirely turned out to be black. Because of that, you can see it just somehow matches to the background. There's a fine line, but it's not accurately visible. This is the drawback of Robert's edge detection, which was resolved in the later stages. But this is all in a part of Robert's edge detection. Hope you guys liked it, and thank you for joining me.